4.1 is a major chapter. It introduces a very prevalent and well-known problem of calculus. It's the tangent line problem. So what we're going to be looking at is using the limits that we have just looked at, and we're going to come up with a way of calculating what is the slope of a tangent line. So our objectives, when you walk away from this, you should feel comfortable with exactly what is the issue with the tangent line problem. You will also want to understand what is a derivative, and that whenever I use the term instantaneous rate of change, I'm looking for a derivative. And then you'll also want to be able to use our past knowledge of limits, apply that to what we call the difference quotient, so that we can calculate the derivative using limits. The first few slides we're going to be looking at a function dealing with displacement. So exactly what displacement is, well, it's when you displace an object, it's when you move it. So we're going to be looking at a change in position or distance over some period of time. And one thing is, we can look at velocity, which is the rate of change in that displacement. So it's actually the rate at which you're moving. So velocity, also sometimes known as the speed. To study this displacement situation, we're going to look at Molly, and we're going to be having her throw a ball up at waist level, and she's going to be throwing it with the original oomph of 18 meters per second. So here's Molly, and what I want you to observe over here is we do have a chart, and we are looking at seconds with respect to the time, seconds for time, and then meters, because in the problem we were talking meters, so the height that we're going to be tracking for her ball that she's throwing is going to be in meters. So here we're going to be looking at very specific times with heights. Obviously when you throw a ball up, there's certain factors that work on it to affect its height. So we're going to be tracking those plot points, graphing them here, and then just overall so you can visually see what's going on. So Molly, I heard you're pretty good at softball. So here you throw the ball straight up. After 1 second, you can kind of see at 0, it was at waist level. At 1 second, or approximately 1 second, it's at about 13.2, so it should be a little higher. Sorry, it's not perfect here. And then 1.8 seconds. Molly, you're freaking out. Stop, Molly. Just hold still. And you missed it. Okay, so that is the track of what exactly is happening with her, with the height, with respect to time of the ball that she threw straight up into the air and straight down. It is tracking that displacement. So you can see from this graph, that is our parabola shape, and so therefore we know we can use a quadratic to illustrate or to model the situation of an object being thrown straight up in the air and down, or an object that's just dropped. The quadratic is going to have where that ball, you can throw it straight up, and it's eventually going to slow down, and then it's going to start falling, and gravity is going to accelerate that so that it's falling even faster. So you get that arc-like shape. But we do know that 3 factors are going to influence the height of the ball, and one of those, of course, is gravity. We use -4.9 if we're talking meters, -16 if we're talking feet. Gravity is the same everywhere, so we're going to be using that same, either one or the other. The other thing that would affect that height of the ball is the oomph that you threw it at, the original velocity that you threw that object at. So that's also going to affect the height. And then finally, obviously if you're standing on top of my desk or if you're standing on the floor, the height's going to be different as well. So that is also a factor that's going to be taken into account to calculate the height. So if I were to look at Molly's situation in particular, we are going to be using meters, so I'm going to want the -4.9, then x squared, plus, and then the original speed or velocity, I really should say, is 18x, and then plus that 1 meter that she was off the ground. So this right here would get us those specific x, y values, or I guess I had, what did I have? TH, so I suppose I should have these as time, because obviously time will influence the height of the ball. like at 0 seconds it was at her waist level. Give it some time, it's going to be either way up high in the air, give it some more time, it's going to be low. So now this is looking at that even further. So I've blown up that parabola. And what I want us to do now is bring it back to that study that we used with calculating the secants and tangent lines. So a secant line, and you'll get the exact vocab for that in a second, is when you take 2 points on a curve and draw a line through it. So what I want us to do is I'm going to let this A point be the 0, 1. Okay, so here's my 0, 1. And then what I'm going to do is I'm going to let x be 0, because that's my original start that I'm looking at. And I'm going to say I want there to be a change in time. So I want to look at what's happening over a change in time. And delta x would be change of x, but we're going to use h for simplicity's sake of some of the calculations that we're going to do. So we're going to let this change in time be 3. So h equals 3. So that brings us to this point right here. And what you would notice is if we wanted to, we could have, well, here was our original, plus that change that I'm looking for, so 0 plus 3, there's where I get my 3. And then if you took that x plus 3, that change in 3 to the original, and plugged it into my function, I would get about 10.9. Go ahead and try if you don't believe me. So what we're familiar with is this used to be what we would call x sub 1 comma y sub 1, and then this would be our x sub 2 comma y sub 2. And if I asked you for the rate of change that was occurring, the average rate of change over from this point to this point, what we would do is we would just say, well, overall, yeah, it did go up and then it went down, but if we took away the up and down and just went straight from here to here, what was the rate of change? So we would take our y sub 2 minus y sub 1 all over x sub 2 minus x sub 1, right? This was what we used to call slope. It was the change in x over the change in y. But this time what I'm going to do is I'm going to say, well, this was just our typical x. If we plugged in, we would have had f of x as our output. So here, what I would look at is we had an x plus some sort of change, so then y sub 2 would be equivalent as us plugging this x plus h into our function and getting the output for x plus h. Okay, so now what we're going to be saying is, well, just like we took y sub 2 before minus y sub 1, what we're going to use is actually f of x plus h, that notation, minus f of x all over, and then the change in x, instead of saying x sub 2 minus, or sorry, x plus h, well, we could, I guess, x plus h minus x, what we really know this as is just that change in x that we established, it's that h. So this right here is the same exact thing. It's our slope formula, but in just a new form. So our new slope formula. And you'll see here I calculated that. So overall what this thing is doing, at 3 seconds, if you started here, just rise 3.3 meters every second and you would have gotten to that point. That's our average velocity of that object moving or being displaced. Alright, this time I looked at this point and this point and I calculated it. So our change of x this time was h equals 1. And so what was the average speed of this ball after 1 second had gone by? And then you can see that it was about 13.1 meters per second. Okay, and that was much faster because, I mean, this had some down to it. So 13.1 meters per second. So finally what I want you to see is between this point to this point, it was at 3.3 meters per second. Here it was pretty steep. Here it was pretty steep. Here it's even steeper. This thick line is what we're going to now look at as our tangent. So that tangent is a very special line. What we're going to be doing is calculating that particular line that's passing through one point. So it's hard because before we had 2 points that we could say y sub 2 minus y sub 1, but now if we were to look at this point 0, 1, Well, the y values are the same, so it'd be like we're taking y minus 1 over 0 minus 0. That's just strange. Okay, so that's where our new formula comes in handy. Okay, and yes, I mean technically the change in x is 0, so h equals 0, but is there a way we can manipulate or finagle our way so that we can actually calculate this by doing our finagling ways of limits, our manipulations? Secant line is related to just a line that passes through 2 points on a curve, and that's what we call the average rate of change. So it's looking at 2 different places, drawing a line, and just averaging out the rate of change. A tangent line is going to be, what if I asked you at one particular point what the speed was? That's what we call an instantaneous rate of change. That's exactly 1 point on the curve. Your line passes through exactly 1 point. The instantaneous rate of change is what we call that. So again, this is our new way to calculate slope, and we add on the limit. So here you can use the limit as h approaches 0 of f of x plus h, and it just makes it a little easier so you don't get these x's wrapped up with each other when you do the overall calculations. And this is what we call the derivative. So a derivative, I will give you that formal definition, a derivative is just the slope of a tangent line. Okay, so this right here is the change in the y values over the change in the x values as before, but just a little bit of a different look. And then we're going to be using our skills with limits to actually get us what we want. Okay, another way, sorry. So secant line, if you let that secant line tend towards, those 2 points tend towards each other, what we get is the tangent line. And then this is our big new one on this slide. Here are different notations that you'll see. It'll say find f prime of x. It will also say y prime, so it uses just that apostrophe symbol. But another way they say it is this is the change d delta x, or delta f of x over dx. So again, that's just, this d kind of represents the change of the function with respect to the change of x. So the change in y over change in the x, and I mean, we technically could have used something like this, but really the d's are what we use most of the time in the book. So these are kind of the ones I prefer, but they're not always the ones used.
So I'm going to do number 8 from your homework set, and I'm actually going to name this f of x just because we've been working with f of x, but it really shouldn't matter. So we are going to say, well, if I wanted to draw a tangent line at the point 2, 1, what would its slope be? So what we're going to do, that's not the best, what we're going to do is we're going to use that slope formula that we just introduced. And again, we want the change between our x's of that, the x's that we choose, we want the change of those x to tend towards 0. So that's what we're going to use. We're simply going to plug in, there's a couple ways you could do it. You could evaluate this and actually let your x be 2, because that's I mean, we're going to be looking at this point and then plus some sort of delta x. But we don't want to have any change, so we're just going to say plus h minus f of 2 all over, and then we would have our h, and then we could solve for this. I'm going to do it the general way, and then at the very end, I will plug back in this x equals 2 value. So I'm going to evaluate this, and then I'll sub in the 2, but otherwise you can evaluate this just the same way. So I'm going to start by saying I want f of input x plus h. So I'm going to take this x plus h and I'm going to input it into my function. So I'm going to get the overall effect of this. 5 minus, and then I'm inputting x plus h into this function. Okay, because it was just like we did with our problems. We would have taken x plus h, whatever it was, and we would have plugged it into our function to get our y value of that second point. Minus, and then we have f of x, which is just this whole thing. So So had we known 2, we would have plugged it in, and we would have gotten our y value. But I'm just going to keep it open to 5 minus x squared. Again, if you're doing it this method, then we would have taken 2 plus h, and we would have plugged it in for our x. Okay, so you would have had 2 plus h here, and then we would have had f of 2, which would have just been 5 minus 2 squared, so it would have been 5 minus 4, so just 1. Okay, because that would have been our y sub 1. Alright, so we have this over h. So then I have the limit as x approaches 0. And then now here's where do not distribute. That is bad, and it will mess this up. So we want to make sure this deserves to be FOILed, so we're going to do that. We have 5 minus, and then in parentheses, I'm going to do this FOILing, x squared plus 2xh plus h squared. And where did all that come from? Again, I just did x plus h times x plus h, and I FOILed that out like it needs to be done. Okay, minus, and then I'm going to distribute this. So I like to look at this as plus a negative 1, and then that way I know I'm just multiplying negative 1 to everything. So plus negative 5 plus, and then I'm going to change this to plus a negative. So that way negative 1 times negative x squared is actually positive x squared. Alright, so this also, this is all over h. This also deserves to be multiplied to everything. So we have the limit. I love writing the limit because I always know that I'm aiming to sub in if I can. So negative x squared plus negative 2xh plus negative h squared plus negative 5 plus x squared all over h. So still can't sub in. That's unfortunate. So I'm going to keep going. At this point, I'm going to now, since I got rid of my parentheses, I'm going to regroup and start crossing things out where I can. And you'll know if you go wrong with these, because what should happen is everything without an h should cross out, and they did. So now I have the limit, and you'll see that the more you work with it, the more beautiful that becomes at the end, that ability to be crossing out everything. Alright. So now, some of you might be afraid, oh no, it's a family, but as long as you're taking from each family, it's going to be okay. So I can technically look at this as in this whole top times 1 over h, right, because this is h over 1. So then you are just going to distribute that 1h shift to every single term, but otherwise you can just say, hey, I'm going to be pulling out an h from everything on the top. So if I do that, I'm going to have negative 2x and then minus h left, right? FOIL that back in or distribute that back in if you want. Those cancel out. And that problem factor that was on the bottom that was not allowing us to calculate the slope of this tangent line has now been eliminated. So we have the limit as h approaches 0 of negative 2x minus h. And here is where we can say, oh yes, I was finding the limit of this, I did my manipulations, now I can directly substitute in, which is always the goal. So I'm going to label this f prime of x equals negative 2x, and we'll see exactly what we found here more as we do these. But now, don't forget, I actually wanted to find the slope at this particular point. So what I can do now is that x was 2. So I'm going to plug in 2, and I'm going to get my derivative, or in other words, the slope of the tangent at x equals 2 was negative 4. And you can even see that. If you look at this point, I'm going to go down 1, 2, 3, 4, over 1, and you can see that's right on. Okay, so there represents a good slope. It was going negative 4. Maybe it was meters per second. Okay, that was the rate of change of this object. Let's say that this was something that was thrown up and it was coming down. That speed of that ball, or I'm sorry, I should say the velocity of that ball, since we're in the negative direction, was in the downward direction, so it was negative 4 meters per second.
So here are our problems. I am going to go ahead and do one of those with you.